So this lecture is about the concept of atomic mass and how it's related to the masses of isotopes and what the percentage abundance is of each isotope. So atoms typically have more than one stable isotope. That is to say, the number of neutrons can be different from one nucleus to another. The number of protons is the same. So we're going to use the example of magnesium here. And we've written the symbols for magnesium for each isotope. So you write the element symbol, and then as a superscript you put in the mass number. And so we can go ahead and figure out, list all the mass numbers for every one of these isotopes. So this is mass number 24, 25, 26. The atomic number is the subscript. It's, you can get that from the periodic table, but if you look at the periodic table, the atomic number of magnesium is 12, so it's always 12, or else it wouldn't be magnesium. Okay, and those are the integers. Now the isotope mass is going to be close to 24, but not exactly 24. So the isotope mass will be a non-integer number. And so we have to actually experimentally determine these. So we need to look up these isotope masses. But you're going to see they're going to be very close to 24. All right, so 23.99. All right, it's just like you know, you see things advertised, it's $23.99. It's really $24, right? So the next one will be 24.99. And the last one, guess what? 25.98. That's the price they put on things when they don't want to think you're fooling them with $24.99 or something like that. All right, so it's $25.98. You can see how close the isotope mass actually is to the mass number. Now, the average weight of all these is what's called the atomic mass. You might hear it called atomic weight, but weight is really the force of gravity on a mass, and so the weight is different on different planets. So we're going to use the word atomic mass instead of atomic weight. But the atomic mass is an average of these numbers. Now you just can't add these numbers up and divide by 3, because that wouldn't be correct, because there's not the same number of isotopes of every one of these. It's not like there's the same number. There's one of these, one of these, one of these. That's what you do if you have 3 objects. Yeah, you can add them up and then divide by 3. But there's many, many more atoms, and they're different percent abundances. So what we can do is we can list the percent abundance, and again, that's something that has to be experimentally determined. Now, most of the time, these numbers are constant throughout the whole Earth. That is to say, the percent abundance for isotopes for magnesium is the same in the US as it is in France or something like that. And so the most stable isotope is magnesium-24, and that's 78.70% abundant. The other two have about 10%. So this is 10.13. And so we could actually figure out what this number is, because the percentages have to add to 100%. And so you might have a problem where you have to find the percent of the missing isotope if you're told that's the last one. So you merely subtract these two numbers from 100 and you can get 11.17%. All right, so the way you do an average for things that have a percent of each object is, first of all, you convert the percent to a decimal number. And so the average is going to be 0.7870 times the value of the mass, 23.99. And you just keep doing that for all of these. And so the next number, 10.13%, is 0.1013. That's times 24.99. And then finally, the last percentage, 1117 times 25.98. And when you do that, well, first of all, the answer should be in the periodic table, because the atomic mass is always put in underneath the element in the periodic table. And so the periodic table says 24.31. Let's look and see what we get from this. All right, I'll be right back. I'm back. All right, so we're going to have to calculate this out since I did not write it down. All right, so 0.787 times 23.99 plus 0.1013 times 24.99 plus 0.1117 times 25.98, 24.31. Hey, I didn't have to do that after all. All right. All right, and so that's how you calculate atomic mass. Now you may have to do a variation of the problem where instead of giving you every isotope and the percent abundance, they might say, okay, what if we don't give you this number? Okay, we don't give you the percent abundance of one isotope. So we say, okay, they don't give you the 11.17%. Well, you can get that number from the fact that 100% minus the others is that number there. And then they'll say, okay, we don't give you the mass either of that isotope. And so let's call that X. But they do give you this number over here, right? And so instead of doing that, they'll give, well, actually you'd be expected to look up the atomic mass in the periodic table, which you would use as the average of all these numbers here. Okay, so just to reiterate, you would have the masses and percent abundances for all the isotopes except one. You find the percent that's missing from 100% minus the other and convert it to a decimal. Use X for the unknown mass, and then use the atomic mass in the periodic table as this number, and then you have to do some algebra. Now the other thing you should realize is that you can get a good guess for what the missing isotope is. If you know it's magnesium-26, then you know the mass is going to be about 26. And the other thing is when you're calculating average, the average can never be smaller than the smallest number, nor larger than the largest number. So these are important checks on whether you're doing calculation right or not.